Okay, so we're going to get into chapter 12, actual business. So we're going to talk about the sampling distribution of the true least square regression line and what you get when you take a sample of that, and how that might inform inference procedures that are coming up. So I really recommend you check out page 739. It walks you through the general concept of a sample regression line, what we've been using in chapter 3. How does it compare to the real, true population regression line? So this is a sample of, this is the real thing. So if you take only 20 eruptions from here, how does that going to compare? So we take random samples of 20 from that scatter plot that we just took. The scatter plots you get will vary. The lines you get will vary. Some slopes will be a little bit steeper than others. So here's an example of 3 sample slopes that got taken, sample equations that, of the line that you get when you sample 20 points out of the entire population. So you put the points on, you get the least square regression line on. Notice they're all different. This one's clustered. So different slopes with different y-intercepts. What we're trying to do is kind of get access to this true line back here. Right, so this is the place we find ourselves. So we're looking at a sampling distribution of the slope. So we're focusing on slope. We're not really interested in the y-intercept so much. Right, so there's a true slope out there. If you sample 100 simple random samples of 20 from the Old Faithful data, here's a attempted simulated sampling distribution. It's not a true sampling distribution, but the different slopes you might get for different samples of 20 Old Faithful eruptions that you might get. So here is a sampling distribution of slope. Notice it's normally distributed. There's a true mean here. It's the approximate sampling distribution because you don't have every single simple random sample here. You just have a simulation of 1,000 of them. So the shape of this is roughly symmetrical and unimodal. The center is going to be the true slope. The spread is going to be interesting when I figure out what's up with that. This is all T-score stuff, T-distribution stuff, so we're into that. So then, the next thing that's going to happen is you're going to look at all of these slopes that you got and check if they're normally distributed. They look pretty good. No real questions. There's a little bit of asymmetry there. So one option here, just to remind you, this is a normal probability plot. This is the last kind of graph your graphing calculator uses. What it does is it graphs the actual slope you got to the z-score within the distribution. If this is a straight line, this is implying that that is normally distributed. The other thing you can do is a histogram of the slopes and kind of notice. Just throw a graph on the normal curve on top of that and see if it fits. So it looks pretty normal. So we have an approximately normal sampling distribution. The center is the true slope. And the spread is going to be a little complicated. So this is the weird thing here. It's the distribution of the population divided by some funky business. So we'll explain that part. So sampling distribution of slope. There's a true equation out there. Instead of having an A and a B here, we have an alpha and a beta because they're fancy in Greek. The mean of the sampling distribution of the slopes that you might get in your sample is the real slope. The standard deviation of the sampling distribution that you get here is a little bit weird. It's the true standard deviation of the population divided by the standard deviation of the x's times root n. So it's standard deviation over root n like we would have done, but we're throwing this little extra thing in there to make it complicated. This is as long as you meet the 10% condition. So just a reminder, 10% condition is about standard deviation always. And the shape is approximately normal if you meet the other conditions. The other way, there's a lot of conditions here. Okay. So it explains the formula. Feel free to read it. But I'm going to summarize what we just found out. In this explaining part of the estimation, the estimation is the estimation of the explanatory variable. When the estimation of the x's gets larger, estimation of the slopes gets smaller. More variability in the values of the explanatory variable leads to a more precise estimate of the slope. It's kind of weird. Sample size, always important. And then conditions are coming. They're almost scary. Okay, so What is the difference between a sample regression line and population regression line? So what we've been using as our model in chapter 3, this is a sample least square regression line. This is the slope and y-intercept that comes out of your sample data, your small data set. Out there somewhere, there is a true actual relationship between your x and your y variable, and that's going to be y hat equals alpha. Oh, you know what, folks? I'm really sorry. I'm not supposed to use a here. This was supposed to be an x. Okay. This is the true y-intercept of the real line for every single data point that is possible to have for the small sample that you have. True y-intercept and the true slope. So fancy Greek letters. What is the regression model when the conditions for inference are met? For slope, B, sample slopes that you might get are going to be centered on the real slope, beta. They're going to be normally distributed if you meet that condition, and this was a little complicated. This was population summation divided by the summation of the x's root n. So just so you know, very bottom of the second page of the formula sheet, we are here. The random variable is your slope. The true center is this business. And this is our summation. Okay. So it is approximately normal with the true mean of beta, the true slope, and a summation of this complicated stuff. Suppose the true regression line for the seating chart study that we just looked at is this, and that the regression model is valid. What is the probability that somebody sitting in the second row will get at least 90 on the test? Okay, so we have our equation. If somebody got a 9, somebody sitting in the second row, so that's the x. So if someone's sitting in the second row, their prediction is broadly speaking 85. Okay, so second row prediction, predicted to get an 85. However, here's where it gets weird, guys. One of the conditions for doing inference along these regression lines is that you're going to assume that if for every x value, the y values are normally distributed around that x value. So that's what this question is asking for. The values of the response variable follow a normal distribution for every single x variable. And the summation, this is the summation of the population summation. So in the second row, predicted to have an 85 as a center. That's what's in the middle, that's what's on the line, but varies by 10. So could have a 75, could have a 95. What's the probability that somebody in the second row will get at least a 90 on the test? So we need a z-score. Yeah. So looking for 90, true center is 85, dividing by 10 is a z-score of 0.5. What's the chance of having a z-score of more than 0.5? You know what to do. It's going to be 1 minus this guy. So it's about 31% chance that someone in the second row gets a 90 or more. What are the conditions? Oh, this is where it gets interesting. Like I said, there are 5 of them. They do spell something. Hopefully, if you want, they may spell almost the word linear, but no, liner. 5 conditions. 1, the actual relationship is linear. Linear relationship. So look at the scatter plot. Check that it's not curving. So that's how you check that one. Check scatter plot and the residual plot. That's a real clue. I'm not making more work for you. You're going to have to check that residual plot anyway. Next, independent. Individual observation are independent of each other. So the scatter plot, that each data point is independent. Those values are independent of the other points. They're not influencing each other. It's kind of conceptual. Might have to do with how you gather your data. When sampling without replacement, check the 10% condition. So 10% condition, that's going to be your 10% condition. Right? 10% condition is actually always the independence condition. Normal. All right, this is shape. For any fixed value of x, the y values are normally distributed. So you're checking that this conceptual thing is true, and the way you're actually going to check that is if we go look at our seating chart example, right? If you're looking at any particular x, that the spread around the line for each of these is about the same, that it's not like dramatically getting smaller this way, that it's not fanning. So I would say for this one, it's fine. It does vary, but it's not ridiculous or consistent, this variation. So about equally wide all the way across, not getting smaller or wider. So this is normal distribution of y's for each x. This is a check the residual plot for sure. So you can get it up there after all. So no fan. Okay. E. Don't remember this one. Equal standard deviation. It's almost the same as the one we just did. Okay. Equal standard deviation for each x. Very similar. Come back to that one. And lastly, everyone's favorite condition. Wait, was this an SRS or was it random assignment? So two of these familiar. Two of these are very familiar. Right. We know this one. This is our 10% condition. We know this one. We just have some extra stuff going on in the middle. The other thing you want to check is, are the residuals normally distributed? This might be a dot plot of your residual, or why can't I spell things? Distributed. All right, what is the sample distribution of B? Accidentally did it up there. Shape, center, and spread. Got it. Oops. What are the three parameters in a regression model? What statistics do we use to estimate them? This is really bizarre. So, this is feeling like it's getting a little out of control. Estimating parameters, AP exam tip. Okay, so when you're doing your z-score, actual slope you got minus the true slope divided by estimation of the slope. Model by normal distribution, however, if you don't have access to this number, which is going to happen to us, you're going to have to estimate the standard error. Okay, so the things that we're estimating, this part, you just get lost. See, sorry about that, guys. If you're lost, it's also because I'm lost. The things that you're estimating about a regression model, there's a true regression model, y equals the true alpha plus the beta x, and there's a true correlation. Guess what? We need a fancy Greek letter for R. It's a rho. How do we estimate these? Well, alpha gets replaced with A, which is your y-intercept for your sample. Beta gets replaced with B, which is your slope for your sample, and then rho gets replaced with R, which you get for your sample. So these are the non-Greek symbols for the true Greek things we don't have access to. we're going to be focusing mostly on this one. What is the standard error of the slope? Is it on the formula sheet? Well, formula sheet, thank goodness, has been updated for the last few years. And now it tells us things we need to know. Oh, look, standard error right there. Yes, the very last thing on page 2. The standard error of the slope is s over sx root n minus 1. This is how much samples of this size vary, which you're going to be throwing into your confidence intervals. How do you interpret it? How much samples of this size, this sample size, vary in their estimates of the slope? On average. For the seating chart experiment, state and interpret the standard error of the slope. Oof. Okay. So, S N. What was our sample size? Don't make me count these, please. Sample size. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. Okay. So this S is given to us in the bottom of the sheet. 10.0678. 73. Sample size was 30, so it's going to be root 29. And then S of x. Oh, me guys, I'm doing this the crazy way. Remember the thing where I said we're going to be reading the rest of this table? The standard error of the slope. Ta-da! Okay. S of the slope. 0.9472 on the printout. Slope, actual slope, the standard error of the slope. So how much estimates of slope vary from samples of size 30 to other samples of size 30? T-score, p-value. Okay. Interpret. Samples of 30 students and their rows and test scores will vary by 0.9472. Now, slope is funky, folks. It has funky units. This was row. This was score. So the slope is rise over row, and so it's score per row, right? Neither of those have units. From in their estimates of slope on average compared to other samples. For example. Okay. So yeah, I actually strongly recommend reading them, but focusing on the car example, not the helicopters. The helicopters is an activity we need to do in class to make it work. What is the formula for constructing a confidence interval? All right. So this is that generic formula we have on the formula sheet. We can start to build it, right? So confidence interval is your statistic, what you got from your study, plus or minus your critical value times the standard error that you got. So our statistic here is going to be the actual slope you got in your study. These are going to be t-scores. So we need a critical value in t. It's a t-star. And the standard error we have up there, I'm going to call it SEB because it's usually going to come from a printout. You may very occasionally need to do this, but it's very rare. So rare I forgot how to do it. See? Okay. So that's how that works. Where do you get the value for t-star? This is a really good review. So let's talk about, so you have a t distribution, which is a curve that is symmetrical and mounded, but compared to a normal curve, there's more data on the edges and less data in the middle. So this is a normal curve. This is a t-distribution with a low degree of freedom, maybe like degree of freedom is 5. And then as your degree of freedom goes up, this is going to start to approach a normal curve. For slope, for scatter plots, 2 quantitative variables, our degree of freedom is going to be n minus 2. So it's you lose 1 degree of freedom for each of the 2 variables. Where do you get the value of t star? You're going to go look at the t-distribution. And the way it's going to work is if you have a 95% confidence interval, you're going to look at the 95% column, which has a tail probability of 0.025, and then you look for your degree of freedom. So if we had a sample size of 30, like we just did for the row thing, that would be a degree of freedom of 28. So this is saying 2.048, and let me explain what that number is about. So if you have a degree of freedom 28, which came from a sample size of 30, what we're saying is if we want to be 95% certain, we want to capture 95% of our data, we need to go 2.048 standard deviations out on this curve. We will then find 0.025 here and 0.025 here. This will add up to 1. To capture 95% on this degree of freedom, we need to go a little more than we would on a normal curve. We need to go further out. It would have been a 1.96. This is a little bit more. All right. So this is the weird stuff. Let's try the actual example, folks.